you see that in the float zone process, the molten zone is travelled basically along the rod. And what should be the doping distribution in float zone process? Float zone process is very important in the sense that it can purify the crystal. It can purify the crystal. How it can purify the crystal? Since this is a molten state, so that means as the crystal solidifies at its progress, what will happen? The impurity concentration will be moved from this region to the top region, because here also there will be rejection, here also there will be rejection. So, that means this end, that is the retreating end, here the carrier concentration or the impurity distribution will be less compared to this end. Why? The same thing will happen, 1/3 will be rejected, say if you dope with phosphorus. If you dope with phosphorus, 1/3 will be rejected. So, here where is the melt? The melt is in the molten zone. So, they will reorganize themselves in such a manner that when it will solidify at this end, 2/3 will be in the molten zone. Then as the molten zone traverse, what will happen? At the end, some amount will be full of impurity. Say this amount, say this portion is of full of impurity, then you chop it off. You chop it off, okay? You cut it, throw it. Again you take this polycrystalline rod or the single crystalline silicon rod for purification. The same thing you do. What will happen? Some of the material will be lost, but during passes, first pass, second pass, third pass, it will be more and more pure, because the impurity will be finally will settle down at this end. So, that is why this float zone technique is very much important technology, not only for the single crystal growth of silicon, at the same time it will give you the purity. For any purification of the crystal, people use this kind of a float zone technique. In float zone, the doping distribution we can calculate. The doping distribution of a float zone process we can calculate. This portion is this zone, that means this is the zone which is moved. Say the initial uniform doping concentration in the rod was C0 by weight, and L is the length of the molten zone at a distance x along the rod. A is the cross sectional area, rho is the specific density of silicon, and S is the amount of dopant present in the molten state, right. C0 is the uniform doping concentration in the rod, L is the length of the molten zone at a distance x from the rod on the rod, A is the area of cross section, rho is the specific density of silicon, and S is the amount of dopant present in the molten state. So, what we can write? We can write that as the zone traverses a distance dx, the amount of dopant added to it at its advancing end is C0 into rho into A into dx, whereas the amount of dopant removed from it at the retreating end is K into S dx by L. Right. As the zone traverses a distance dx, the amount of dopant added to it at its advancing end is C 0 rho A dx. What is A into dx? Volume. Then rho is density. So, volume multiplied by density is mass. So, C 0 is per gram. C 0 is the amount of say phosphorus per gram of silicon. C 0 is the amount of phosphorus say per gram of silicon. So, how much gram of silicon is there? Rho into A into dx. So, what is the concentration? Concentration is C 0 into rho into A into dx. Yes. Whereas, the amount of dopant removed from it at the retreating end is K into S dx by L. S, what is S? S is the amount of dopant present in the molten state. Present in the molten state, you see that it is amount of dopant present in the molten state. It is amount of dopant present in the molten state. Okay? And dx is the length where this happens. So, that means dx by L multiplied by S is the amount of dopant present in this length, which when multiplied by K will give you the amount of dopant removed from it. What is K? K is the segregation coefficient, that means Cl by Cl. K is Cs by Cl. Okay. So, when you put K multiplied by Cl, here Cl is the concentration in the liquid state, molten state, we have taken it as S, and since the length is dx, so S dx by L, right. So, now we can write with this expression that ds is equals to C 0 rho A dx minus K S by L dx, that is equals to C 0 rho A minus K S by L into dx, or integration 0 to x dx is equals to S 0 to S ds by C 0 rho A minus K S by L, where S 0 is equals to C 0 rho A L is the amount of dopant in the zone when it was first formed at the front end of the rod. Yes. I have calculated ds, which is the difference between these two amount of dopant, one in the advanced end, another is the retreating end, and then we make use of the integration to calculate for the whole rod, and for the x we have taken the limit as 0 to x, and for ds we have taken the limit from S0 to S. S is we know is the amount of dopant present in the molten state, but what is S0? S0 we have written as C0 into rho into A into L is the amount of dopant in the zone when it was first formed at the front end of the rod, that means at the beginning, that we have assumed. So, with these limits we can make some small mathematics, and you will find that the result will be like this. Should I work out the whole expression, or I should give the result only? As you like, I have no problem. It's the choice is up to you. Whole expressions? Okay, let me deduce. Absolutely, there is no problem. So, the expression is this: integration of dx, this is our final expression on which we shall work out, Let us take this as equals to t, C0 rho A minus Ks by L equals to t. So, let us write that this is equals to t, C0 rho A minus K S by L equals to t, or yes, dt equals to minus K ds, K by L into ds, K by L into ds, or x equals to minus L by K dt by t, So, that is equals to minus L by K ln t. Then put the value of t, minus L by K into ln, what is the value of t? Rho 0 C 0 rho A minus K S by L, then put the limit S and S 0. It is okay. Or from this expression, or K x by L, that is equals to minus of ln C 0 rho A minus K S by L plus ln C 0 rho A minus K S 0 by L. Can I write? That is equals to ln C 0 rho A minus K S 0 by L by C 0 rho A minus K S by L. This is equals to ln S 0 by L minus K S 0 by L by S 0 by L minus K S by L. What I have done? No, we have assumed that S 0 equals to C 0 rho A L. So, I have put the value of C 0 rho A as S 0 by L. Can you remember that we have taken the value of C 0? You see that here S 0 was taken at C 0 rho A into L. So, what is the value of C 0 rho A? S 0 by L. So, I have put here S 0 by L, C 0 rho A. that is equals to ln 1 minus k by 1 minus k into S by S 0, right. Next stage is or 1 minus k into S by S 0 by 1 minus k equals to e to the power minus k x by L. Why minus is there? E to the power minus? It is because here in the denominator it was S by S 0, I have changed here to the numerator S by S 0. So, it becomes e to the power minus k x by L, or 1 minus k into S by S 0, it is equals to 1 minus k e to the power minus k x by L, or k into S by S 0, it is equals to 1 minus k e to the power minus k into x by L, or S equals to S 0 by k multiplied by 1 minus k e to the power minus k x by L. So, now if you put the value of S 0, which is given by C 0 rho into A into L, you will get C 0 rho A L by k into 1 minus k e to the power minus k x by L. So, this is the doping distribution of a float zone process. This is the doping distribution of a float zone process, and you see that S is the amount of dopant present in the molten state. S is the amount of dopant present in the molten state, and C 0 is the uniform doping concentration in the rod at the starting C 0. Rho is the specific gravity, A is the area of cross section, L is the length, K is the effective segregation constant. The other things you know. Now, this K, value of K, you know that K is C S by C L, right. But we have assumed that when it is rejected to the melt, there is a melt and almost 2/3 is being rejected to the melt. So, during rejection, what happens? Does the impurity uniformly distribute throughout the melt or not? Does the impurity instantly diffuse through or distributed throughout the melt or not? Because you see that there is a 60 kg melt or 100 kg of melt is there in the crucible. So, if there is a 60 kg or 100 kg of melt, and when it is rejected, where it is rejected? It is rejected at the interface between the solid and liquid. If 2/3 is rejected, then at that point where the pool starts, pooling is being made at the liquid solid interface, and the rejection is going to be held in that interface only. The rejection is also going to be held in that interface only, because the pooling is not through the whole mass of the molten state, it is from a single point. It is from a single point. So, the rejection is taking place in the single point only, and instantly it cannot diffuse throughout the whole mass uniformly. So, that means there is a problem inside the molten state so far as the impurity distribution is concerned. That is why one term which is known as the effective distribution constant or effective segregation constant is used. This K is the effective distribution constant, taking into account that it is not uniformly being distributed throughout the mass of the molten state. So, that is a concept, we have nothing to do with so far as the solving of the problem is concerned. There we take simply Cs by Cl without going into those intricacies. And if you take the silicon as an example, you will find that different kinds of doping has different levels. Say this is the antimony, phosphorus, arsenic or carbon, platinum, etc., oxygen is there, and those are all, since this is the conduction band, this is the valence band. So, all will give rise to donor level. It will donate electrons, and these are the ionization energy 0.039, 0.45, 0.54, etc. Those are the ionization energies. Similarly, for acceptors you see that boron, aluminum, gallium, indium, etc. those are the ionization energies. So, different materials has different ionization energies. And another thing you see that this D stands for donor. So, that means this carbon, though it occupies 0.35 electron volt above the valence band, it acts as a donor for silicon. Similarly, platinum D. On the other hand, you see that oxygen for 0.38, it acts as acceptor. Unless otherwise it is written by A or D, it is basically near to the valence band, it is the acceptor, nearer to the conduction band, it is the donor, unless otherwise mentioned. And all these energies are in electron volt. So, if you analyze the band gap of the silicon, inside the band gap you will find different kinds of levels, and those levels are due to different kinds of doping concentrations of different elements, and these are the elements. This is the mapping of the band gap basically. All those levels are there inside the band gap. Remember that within 1.12 electron volt all those levels will be there. Okay, now another type of doping I must introduce, that is known as the neutron transmutation doping. Diffusion type of doping you have acquainted with. Then there was ion implantation. Here this is the third type of doping which is used for silicon, it is known as the neutron transmutation doping. In neutron transmutation doping, the whole wafer is irradiated with neutrons, thermal neutrons obviously, in an atomic reactor to dope phosphorus in silicon. So, what is the methodology? Methodology is that you take silicon, you put the silicon wafer, then you irradiate the silicon wafer with a thermal neutron. So, what will happen? 30 will be 31, 30 will be 31. Why it will be 31? 1 and 0 neutron. So, it will be 31, and this 31 basically is a radioactive form with a half life of 2.62 hours. So, within 2.62 hours it will be transformed into phosphorus 31p15 with the emission of a gamma ray, and when phosphorus will be there, there will be an emission of beta ray. So, first with neutron bombardment or irradiation, normal silicon will be converted to radioactive silicon, and this radioactive silicon will be converted to phosphorus with the emission of a beta ray within 2.62 hours, because the half life is 2.62 hours. So, what you find that if you take the whole silicon wafer and irradiate it with neutron, what is the penetration rate of neutron in silicon? It is almost 100 millimeter, it is very high. Neutron can penetrate throughout the length and breadth of the silicon wafer. So, in our case what is the thing? It is almost 300 400 micron. So, you will find that the silicon inside the wafer will be fully irradiated with neutron, and that will be 30 silicon to 31 silicon, and then the whole 31 silicon will be converted to phosphorus. That means, you see that very uniform doping will be there in the silicon wafer. The whole wafer will be uniformly doped. Homogeneous distribution, this assures homogeneous distribution of the phosphorus dopant resulting in uniform doping. Where this is used, the whole wafer is used in some power electronic device, the whole wafer. If the whole wafer is used, that means the doping distribution must be uniform. In normal IC technology, we use only a piece of the material. So, if there is a degradation of it, if there is some dislocation type of thing, or if there is a problem in the doping, you can avoid that portion. But where the whole silicon is used, you cannot avoid any portion to remove from the host wafer. So, in that case, the neutron transmutation doping is resorted to, using which the whole wafer can be uniformly doped with phosphorus. Then we come to the second issue of gallium arsenide crystal growth. Till now we were in the discussion of silicon crystal growth. In silicon crystal growth, we find that there are two types of methodology used, techniques that are used. One is Choralsky technique, another is the float zone technique, and there if you can compare those two techniques, you will find that in Choralsky technique generally a crucible is used, in float zone no crucible is used. In Choralsky technique the resistivity is less, in float zone technique the resistivity is high, but float zone technique crystals grown by float zone techniques, those are used in power electronics, discrete power device, not in IC technology. In IC technology, it is the Choralsky technique which are used, and almost 90% of the silicon wafer which are used in the electronic industry are grown by the Choralsky technique, right. Then for gallium arsenide, one technique we shall introduce, it is known as the Bridgman technique, BRIDGMAN, Bridgman technique. In Bridgman technique, we use two zone furnace. Two zone furnace, you see that is, it is zone 1 and it is zone 2. Two zone furnace is used. If you take the profile of the furnace, this is the profile of the furnace. In zone 1 the temperature is nearly 600 degree centigrade, in zone 2 it is 1242 to 1260 degree centigrade, right. So, what we use a two zone furnace. In zone 1 the profile shows that the temperature is less compared to the zone 2 profile. Then you take one quartz crucible, this is a quartz crucible inside which there is a quartz boat, this is a boat. On the boat you take gallium, and inside the crucible at one end where the temperature is low, you put some arsenic, it is sealed, remember this quartz tube is sealed. Inside the quartz tube there is a crucible, it is a the shape is boat like. So, we take a quartz tube inside which there is a quartz crucible boat, on the boat there is gallium and there is arsenic at one end of the quartz tube. Why this arsenic is there? you know that what is the melting point of gallium? The melting point of gallium is 1238 degrees centigrade, 1238 degrees centigrade, and at that temperature the surface of gallium arsenide will decompose into gallium and arsenic, because the melting point of gallium is very, very low, because it is liquid at room temperature, and arsenic melting point is also low, it is 600, almost 610, 620 degrees centigrade. So, before reaching to the melting point of gallium arsenide, which is 1238 degrees centigrade, you will find that the surface is going to dissociate. There will be decomposition into arsenic and gallium. So, there will be loss of arsenic. Why? The decomposition rate of arsenic is faster than the decomposition rate of gallium. So, that is why arsenic is kept so that any loss of arsenic will be compensated by the over pressure of arsenic. So, always gallium arsenide is grown using some over pressure of arsenic. That means, some saturation of arsenic must be there in the environment, so that any loss can be compensated by the arsenic, which is kept at one end of the quartz tube. So, first you keep here gallium and you keep here arsenic, then what will happen? Arsenic vapor will be produced, and here also gallium is there. So, there will be gallium arsenide synthesis. First part is the synthesis, not the single crystal. Our aim is to grow the single crystal, but first you have to synthesis gallium arsenide polycrystalline material. So, either you can use this apparatus, you take this apparatus, you take arsenic and gallium, then you heat it so that gallium arsenide will be there, or you can synthesis gallium arsenide in a separate apparatus and put it in the boat, either of the two. Either in the boat you can put gallium arsenide, or you can put gallium and place arsenic a little bit on the other side where the thermal profile is very, very low. Remember that this arsenic is kept to create some over pressure of arsenic, so that any dissociation of arsenic from the surface of the gallium arsenide, even if takes place, the crystal does not have any loss of arsenic, it is compensated by the arsenic over pressure, right. Then what is done? A seed crystal is placed here as usual, and the heater is moved. This heater is moved, you see that there is a direction of heater travel. So, as the heater is moved, so this portion where the seed crystal and the melt is there will be a thermal gradient. That means, the because of the difference in temperature, it will solidify, it will freeze, and eventually as the heater progresses, the whole melt will be converted into single crystal of gallium arsenide. So, it will depend on the temperature profile, and that can be controlled very efficiently and conveniently using a computer. You can check how much crystal is grown, that can be done using some optical microscopy. Then you can take the weight inside, so that the rate of growth can be calculated. If you see that the rate of growth is very high, you can less it easily, you can decrease, you can reduce it, or if it is very low, you can make some faster kind of growth. Also, you can check the dislocation density inside the material. Everything can be investigated during the growth process itself. So, accordingly you can change the parameters of different kinds of growth. So, you will find that after the whole direction, after the whole melt is solidifies, there will be a single crystal of gallium arsenide. What will be the shape of this gallium arsenide single crystal? D type. It will be D shaped, because the boat is D shaped. The boat is D shaped, because the melt will be converted to the crystal. Melt will be, because there is no pool, remember, here there is no pool. If there was a pool, then you can convert it into a circular shape, but there is no pool. Here only the heater travels, it starts from this portion and it ends here. So, eventually when all the melt solidifies, you will find a D shaped type of crystal. So, we can summarize that the growth chamber consists of a horizontal quartz tube, at one end of which there is a quartz crucible containing gallium arsenide melt kept at temperature of 1238 degrees centigrade. Why 1238? Because the melting point of gallium arsenide. The other end of the crucible is cooler, it is kept at 617 degrees centigrade. This thing, it is kept at 617 degrees centigrade, it is cooler, and contains small quantity of arsenic. This arsenic produces overpressure of arsenic that controls the stoichiometry of the gallium arsenide melt. Controls the stoichiometry of gallium arsenide melt means any dissociation of arsenic from the gallium arsenide surface can be compensated by the extra gallium which you have kept at one end of the quartz tube. Right, here we have already discussed that two zone furnace is used, left zone to maintain required overpressure of arsenic and right zone just above the melting point of gallium arsenide where the growth takes place. As the furnace is moved towards the right, you see that the furnace will have to be moved towards the right. Why? Because melt is here and the seed crystal is placed here. So, you have to move from the seed crystal towards the right direction. Is moved towards the right, the melt cools at one end where a seed crystal is placed to establish a specific crystal orientation. Gradual freezing of the melt or solidification makes a single crystal of gallium arsenide. It is very simple technique. And there is one modification of this horizontal Bridgman technique. It is known as the horizontal Bridgman, because you have kept in a horizontal direction and you are moving the heater in the horizontal direction. It can be vertical also, so that the movement of the seed crystal takes place in the vertical direction. From horizontal direction, suppose this is your horizontal quartz crystal, you can move into the vertical direction. In vertical direction, in this case you can use a pool also. In horizontal vertical in vertical Bridgman process, if you give a pool, then the shape will be circular in nature. Now, why we are interested in shape? It is D shape, it is circular shape. Ultimately, we need circular shape wafer, because the process technology is based on the circular shape wafer. And if you have a D shape material, to make it circular shape, what we have to do? Yes, so material will be lost, there will be huge loss of material. If you make a D into circular shape, so loss of material will be there, and loss of material of such high purity grade. So, you think that the costing of the wafer will be very high, because you will add those material loss etc., and the labor cost etc., in the end product. So, if there is a D shaped crystal, the costing will be higher than the circular shaped. So, like horizontal Bridgman, you can have vertical Bridgman, and you can imagine what should be the strategy for a vertical Bridgman. You keep the gallium arsenide in the quartz crystal tube, you put a seat and the seat can be pulled using some pulley arrangement. You need not to pull by your own hand. There is some mechanical pulley arrangement using which the pull can be made, some motor is there. So, motor will pull and you can adjust the pull rate by using some microprocessor or microcontroller type of control arrangement. And what is the rate? The rate is in some cases 1 millimeter per day, 1 millimeter per day, 2 millimeter per day. So, that means for the growth of a large crystal several days are required, because the pull is very slow, to avoid any jerking or any mechanical movement, so that the dislocation can be kept in a minimum value. If there is jerking, if there is mechanical movement, then it will be very prone to dislocation or other kind of defect. Another thing is that the temperature is very high. So, you have to reduce the temperature. So, when the pull starts, basically the temperature is also reduced, that is by the radiation method. So, if you can pull very high in a high speed, so the cooling rate will not be very high. So, your crystal will be some thermal dislocation will be there, thermal jerking will be there, and that thermal jerking will give rise to dislocation. So, in horizontal bridgement, what we think or what we see that there is a mechanical movement of the melt, not actually the melt, but the heater. The mechanical movement of the melt through the gradient is replaced by slowly reducing the temperature of the growth region electronically. Let us go to this picture. You see that here there is a mechanical movement of this arrangement, the lower portion have some mechanical movement, or you can move this quartz crystal, a quartz tube in this direction, either of the two. So, there will be some movement. So, you can, why the movement is required? Because for freezing you need low temperature. So, that means you have to shift either the heater or the melt, then only between the solids and the liquid interface it will be solidify, because the temperature gradient must be there, there will be less temperature, then only it can solidify, otherwise it will remain as a melt. But if you can avoid the mechanical movement, you can slowly reduce the temperature of this junction electronically. By using a computer control, you can change the temperature, okay, slowly reducing the temperature of the growth region electronically. That is known as horizontal gradient freeze method, HGF. HGF, that is the horizontal gradient freeze method, where there is no mechanical movement is done, electronically the temperature is reduced slowly. Now, what are the advantages of this horizontal gradient freeze method? In horizontal gradient freeze method, the advantages are you need less space. Why the less space is involved? Because there is no movement of the heater or the melt. For movement you need some finite space. For movement you need some finite space, because you can start how much the length is. The length can be 12 feet, 16 feet, 10 feet. So, that means if you can start from this position, you have to movement from this here, from there, say movement of say 20 feet is involved. But if you can reduce the temperature electronically, then you need not to use some space. Electronically you can change the temperature, you can cool down. And another is less sensitive to mechanical disturbance. Any mechanical disturbance will give rise to the dislocation, the defect inside the crystal. So, these are the two advantages. You can have using horizontal gradient freeze method. This horizontal gradient freeze method is nothing but an improvised horizontal Bridgman technique, where the mechanical movement is avoided and electronically the temperature is reduced. We have discussed this thing that the D shape of the grown crystal. So, when the wafers are made of circular shape, considerable loss of material is incurred. Both in horizontal Bridgman and horizontal gradient freeze grown gallium arsenide, both are contaminated with silicon atoms from the quartz tube, and thus the grown crystals become N type. That is another problem, because at this temperature, what was the temperature we find? 1238 degrees centigrade. So, if you use silicon crucible, so silicon will be diffused from the crucible inside the gallium arsenide. But for gallium arsenide, silicon is an N type dopant. So, your material will be N type. So, you cannot grow using this technique, the P type material, or one very important type of compound semiconducting crystal is there. It is known as the semi-insulating. Semi-insulating. SI, semi-insulating gallium arsenide. Okay. So, it can be N type, it can be P type, it can be semi-insulating type. Remember that for silicon or germanium, semi-insulating type is not available. Semi-insulating type means very high resistive sample without any doping, without any doping. So, what is the advantage? Advantage is that for epitaxial crystal growth, you need a substrate. Suppose you are using an N type substrate and you are growing a gallium arsenide layer on gallium arsenide substrate, or aluminum gallium arsenide layer on gallium arsenide substrate. Then if you want to measure the electrical parameters of your grown layer, what will be there? There will be sufficient contribution from the substrate, because substrate itself is either N type or P type. Your substrate is either N type or P type. So, for measurements of electrical characteristics of your grown layer, that substrate will contribute to the electrical parameters, right. Suppose you have grown this material, it is itself N type, and you have made some layer on it, epitaxial layer, and you want to evaluate the electrical property of the epitaxial layer. Electrical property means, suppose you want to know what should be the resistivity and mobility of your grown layer. So, can you decouple the mobility of the substrate and the layer? It is very difficult. But if you can grow the epitaxial layer on a semi-insulating substrate, then what is the advantage? Advantage is that semi-insulating means it is very high resistive, it is almost insulator. So, that means it will not contribute to the electrical property of the grown layer. So, that is why generally this kind of epitaxial growth takes place on semi-insulating substrate, so that the substrate has no effect. Then why we use the substrate? We use the substrate for lattice matching. We use the substrate for lattice matching, so that the epitaxial layer is a very good single crystal thin layer, but we do not want that the substrate electrical or other properties is percolated or moved to the epitaxial layer. So, that is why the semi-insulating substrate is used in some cases, and you find that since the quartz tube is made of silica, so there will be N type property of the grown layer. So, what is the way out? The way out is that you can use pyrolytic boron nitride crucible, pyrolytic boron nitride crucible instead of quartz, but it is very costly. It is very costly. So, that is one disadvantage of the Bridgman or the gradient Fritzsche method, horizontal gradient Fritzsche method. Here at this point we can discuss the advantages of Chodorsky technique for gallium arsenide crystal growth. We were in the Bridgman. Now, if we discuss the advantage of Chodorsky technique, you will find that in Chodorsky technique, apart from anything, it will be round shape, the circular shape, because the crucible is circular in nature. This is first advantage. And second advantage is the ingots is circular cross section. Second advantage is due to the rotation of the melt, efficient mixing of the host and dopant is done, because you have seen that in Chodorsky technique there is a movement, rotation is there. So, because of the continuous rotation of the crucible, the mixing becomes uniform. Such type of advantage is not there in case of Bridgman technique, because there is no rotation of that sense in case of Bridgman, only the horizontal movement is there, but in Chodorsky continuous movement is there. So, the mixing of the host and the dopant. In gallium arsenide, what is the which one is the host? Gallium arsenide is the host, obviously. Another thing is that large diameter crystal can be grown, which is not possible using Bridgman technique. High yield, that means very large, and in situ synthesis of the compound. In situ synthesis of the compound means gallium arsenide can be formed inside the crucible itself. Gallium arsenide synthesis is possible. One thing I must mention here, that normal Chodorsky technique is not used for gallium arsenide growth. Normal Chodorsky is not used. Why? Because of the degradation problem of arsenic from the melt, right. Then what is used? One material is used which is known as B2O3, boron trioxide. Boron trioxide is a liquid type of thing at that temperature, which does not react with gallium arsenide. It acts as a cap on the gallium arsenide melt. So, if this is gallium arsenide melt, you cap it with B2O3. It will not react with gallium arsenide. B2O3 is not reactive in that sense. So, what will it do? It will prevent the loss of arsenic from the surface of the melt gallium arsenide, right. That is why it is known as the liquid encapsulated Chodorsky. It is known as liquid encapsulated Chodorsky, LEC technique. When the partial pressure of one or both components are large, that means gallium or arsenic, the melt surface must be protected either by incorporating an independent source of the vapor under dissociation. If you compare with horizontal Bridgman or horizontal gradient Fritzsche, you see that it is independent source of vapor means some arsenic is kept at one end of the quartz tube, you remember, or by other means. Other means you have to cap the surface of the melt. You have to cap the surface of the melt. In liquid encapsulated Chodorsky, the surface is covered by B2O3. It does not react with gallium arsenide, but reacts with silica crucible. That is another problem. It reacts with silica crucible. So, graphite crucible or pyrolytic boron nitrate crucible is used. That means, if you use B2O3, you should not use the silica crucible. You have to use either graphite crucible or pyrolytic boron nitrate crucible. Otherwise what will happen? It will react with the silica, right. So, in liquid encapsulated Chodorsky, what you find that at the temperature of the at melting point, the surface will have loss of arsenic. the surface will have loss of arsenic. To prevent that, you have to cover the surface with B2O3. You have to cover the surface with B2O3. In horizontal bridgement or horizontal gradient fridge, what we have seen? We have kept arsenic at one end of the tube to compensate the loss. Here we use a cover of B2O3. Remember that. That is why it is known as liquid encapsulated Cholesky. We have encapsulated the melt using some liquid, and that liquid is B2O3. Only one care must be taken, that in B2O3 you should not use the silica crucible, you have to use either graphite or pyrolytic boron nitride. And here as well as usual, the doping can be made by silicon, tellurium or selenium for N type and zinc and cadmium for P type. For semi insulating, it is almost undoped, but in some cases iron or chromium is doped. For silicon, we have used phosphorus or arsenic or antimony for N type and boron or aluminum for P type. Here we use zinc and cadmium for P type and silicon, tellurium or selenium for N type, right. And one more type I have introduced, it is the semi insulating type, that is undoped in nature. Okay.